how much faster would you be able to get to your bus stop if you could go straight through things like buildings and cars? Let's look at how to find resultant vectors graphically today. Welcome back to Fast Physics. Once again, I'm Maggie, and I'm definitely not an expert in physics. Today, we're going to be looking at how to find resultant vectors graphically. Now, what exactly are vectors, and what is a resultant? Well, vectors represent movement and have both magnitude and direction, which we can represent as the length of an arrow and the direction that it points in. Next, a resultant is the combination of several vectors. You can think of it this way. If you're walking to your bus stop, you probably can't take the shortest possible route there because you have to go around things like cars and buildings. So your journey can be represented by a bunch of shorter vectors, each of which has a unique magnitude and direction, and represents a portion of your journey when you are moving in a certain direction. To find your displacement, which is your change in position, and the resultant vector from all these little vectors, we can look at the map and just draw a line from your final position to the place that you started. So in the same way, when we try to find the resultant of different vectors, we can graph them on our coordinate plane first. When we graph vectors, we always line them up head to tail, with the first vector's tail starting at the origin. Then we draw in the other vectors, taking their directions into account as we do that. While their directions matter, the order in which we draw them doesn't matter. In the same way that we can add 5 numbers together in whatever order we want because of the commutative property, we can draw the vectors in whatever order we want to. After we're done drawing the vectors in, we can draw our resultant vector in as an arrow starting at the origin, where the tail of our first vector is, and ending at the head of the last arrow. We can find the resultant vector's magnitude by measuring how long it is, and we can find its direction by measuring how many degrees it is from the x-axis by using a protractor. So now that we know how to do that, let's try finding the resultant vector from my last video, where I introduced two-dimensional movement. On the track from that video, we first traveled 40 meters north before turning to travel 30 meters east. If we were to find the displacement, we would first need to label our axes accordingly. We can label both in meters, since that was the unit mentioned in the problem, and then we can label the positive half of the y-axis as north and the positive half of the x-axis as east, because that's how they're usually arrayed on a compass. So that's 40 meters north and 30 meters east. 40 and 30 meters are the magnitudes, and north and east are the directions. Because both vectors are in cardinal directions, which are our axes, we know that our 30-meter vector, which is 30 units long to represent its magnitude, will be 0 degrees from the x-axis, or exactly east, and our 40-meter vector, which is 40 units long for its magnitude, is at 90 degrees from the x-axis, or 0 degrees from the y-axis, or due north. The first one is easy to graph because we know that it's parallel to the x-axis, and actually on the x-axis because it starts at the origin. We graph the second by using a protractor to find 90 degrees, and drawing the vector in at the head of the first. Our resultant would be this vector here, drawn between the tail of the first vector and the head of the second vector. As you can see, drawing the vectors in a different order wouldn't change the resultant vector at all. Both its length and direction are the same, which means that its corresponding magnitude and direction are exactly the same as well. Whichever way we draw it, we find that our resultant vector has a magnitude of 50 meters and a direction of 53 degrees north of east by looking at our line here. It has a length of 50 units, which represents 50 meters, and we find its direction by measuring with a protractor to get 53 degrees. Because the reference point of the 53 degrees is the positive side of the x-axis, which as we said earlier represents east, we know that the direction is 53 degrees from east. Since we also know that this side of the y-axis is north, we can say that it's 53 degrees north of east. Let's try another problem with some more vectors. What's my displacement if I travel 20 meters northeast, then backtrack 10 meters, then travel 40 meters 25 degrees south of west, and finally 30 meters due north? Since we know that the problem is once again using north, south, east, and west, we can label our graph the same way that we labeled our last one. So let's take a look at the vectors involved. We have 20 meters northeast, which we can represent as a 20-unit long arrow, pointing 45 degrees north of east. Since we know that northeast is exactly halfway between north and east, which are 90 degrees apart, then we have 10 meters backtracked. Now, what exactly does that mean? When we draw that vector out in two-dimensional movement, it's just a vector that's in the opposite direction, and it's equivalent to subtracting a vector. Just like something that has a negative slope is traveling in the opposite direction of something that has the same slope but positive. Subtracting a vector or backtracking just means drawing in the vector in the opposite direction than it would have been otherwise, but with the exact same magnitude. So in this problem, the vector would have been pointing northeast, but we now know that it's pointing southwest, or in the opposite direction of northeast. Our last two vectors are pretty easy to find. 40 meters 25 degrees south of west is a 40-unit arrow 25 degrees off of this side of the x-axis, and 30 meters due north is a 30-unit long arrow pointing straight up the y-axis, which is north. So we can draw them on our graph now. 45 degrees at the origin, 20 units long, then back toward our origin 10 units, then use our protractor to find 25 degrees south of west for 40 units, and finally parallel to the y-axis for 30 units. Once again, it doesn't matter what order we draw the vectors in. In fact, if we draw the first two vectors non-consecutively, it might actually be easier to see them. Either way, when we connect the head of the last vector to the tail of the first vector, we get the same exact result in. So this is a really easy way to find both the magnitude and directions of resultant vectors, right? But I hope that you guys can see that the main flaw of this method is that it's super reliant on how accurate the things that you're measuring with are. If you make a mistake measuring or with your measurement tools, it'll be incorrect. However, it does give us a pretty good idea of the range in which the resultant's magnitude and direction are for when we start to look at it analytically, which we'll be looking at in the next two videos. Be sure to turn on post notifications to find out when they come out, and thank you for watching this video. Bye!